recording. So there are some. Okay. So yeah. So the video will be available, and also whatever I'm saying, it will be pretty much there. I mean, I think you can just take a look at it later. So that, yeah, that's the best thing. Okay, good. So the idea was to solve decision problems in mathematics and logic. And the idea is that when you have a specific, let's say a logical formula, right? A logical formula phi, and then you want to see if this formula phi is satisfied. Okay. And how do you check that? We would reduce this problem into checking emptiness of automata. Okay. And so the main problem was actually this thing about logic. So we would like to check certain decision problems in logic, and in order to do that, you would reduce those problems into emptiness of automata. Okay, and these were well-known works by Büchi, Rabin, McNaughton, and so on. Okay, so these were well-known works in the 60s and so on. Right. Now, these are used for specification and verification of infinite objects, where you have a finite set AT of, I would call them atomic propositions, right? And the system states, right? So these are the system states. So they can be labeled with some, you can say there is a label from the states to a set of action proposition. So each set has a label, and what is the label? So the label is a set of action propositions. Okay. And the computation, so the computation of these automata or the computation of these systems, these are infinite word over this set of action propositions, right? So what is my alphabet here? So the alphabet is this one, right? So the alphabet is this. Okay. Now, as I was saying, that questions about satisfiability and correctness of specifications, they reduce to emptiness and language containment of automata. Why language containment? The reason being, like, so I have the system and then I have the specification. So I can also consider the specification also to be a set of words. That's also a language. So if the system is correct, that means all the executions of the system is included in the language of the specification. So that is like, that corresponds to language containment. Clear? Okay. And when you are talking about language containment, like, so for example, when you say A log A is a subset of A log B, how do you solve this in general for an automata? I mean, for given two automata A and B?
What do we have to do? Like decide if the language is.
Yeah. So if language of A is a subset of language of B, right? If you are given, let's say, two DFA here, A and B are two DFA, how do you do that? So you are given two DFA, A and B. You want to check whether the language of A is a subset of language of B. How do you do that?
Like it will fail if there is a word which is accepted by A and rejected by B or vice versa.
Yeah.
So maybe we can create a product of both the automata.
Uh-huh.
Then the accepting states will be the ones which are accepted by exactly one of the automata.
So then it is more like you are talking about union, right? It's accepted by one of them, then it's like it's accepted either by this one or this one. So how do you do this thing? Like how do you do, for example, like this is a set, right? This is a set of words, this is a set of words. So how do you do like language of A is a subset of language? How do you say that set containment in general? Like one set is contained within another if and only if.
Complement.
Yeah, complement of which one?
Complement of A is contained in.
So this is the thing, right? A of A intersection A of B complement should be empty.
Yeah.
Correct? And how do you construct this? So this is like you can take a product of the two automaton, check for their intersection, like product of which automaton, this automaton and this automaton. So, and then you check for their emptiness. Right? So this is the thing. And so again, for the online participants, you can also participate, and I mean, whenever there is a question, just feel free to either answer, or if you have some questions, just feel free to stop me. Okay, so this is the thing. So what we were saying is that essentially you can reduce the problem of satisfaction. Okay. Right. Thanks. Okay, there are more people, it seems. Okay, good. Okay. Now, just like the way we define an automaton over finite words, we are now going to define an automaton over infinite words, right? So usually when we are defining an automaton over finite words, what are the components that we would have?
The state, transition, initial state, final state.
What else?
Letter.
Yeah, there's an alphabet, right? So here also we would consider the alphabet to be a finite set. So we would have a finite alphabet, which is sigma. And then we are going to consider infinite words, right? As I was saying, these are omega words over sigma. And then, so the set of all infinite words over sigma, it's denoted by sigma omega, right? And the language, which is a subset of the set of all infinite words, it is a subset of sigma omega. Clear? And if I consider, for example, like let's say my sigma is AB, then I can consider, let's say, some L here, which may be of the form AB omega. So what is this? Like AB is repeated infinity of, right? It's just a single word here, which is AB repeated over and over again. And so in general, as I was saying, that when we are going to talk about a specific system, our sigma is going to be of this form, right? So the states would have labels which are set of atomic propositions. Okay. And if I consider a prefix of, let's say, a W, which is an infinite word, then this W belongs to sigma's W. It's clear? Because it's a prefix, it's a finite prefix. So that has to belong to, it's a finite word. So it should be in sigma's term. Okay, good. So now I will define something called a Büchi automaton, right? So you have all looked at NFA and DFA. So we are going to talk about this automata over infinite words. And there are different kinds of automata over infinite words we will be looking at. So we'll start with this kind of automaton, which is called the Büchi automaton. right? So what is okay, so here just like finite state automaton, we will have q sigma delta q0 and f. So where q0 is a subset of q, right? It's a set of initial state. So when I'm saying that q0 is not necessarily singleton, it means that it can be a non-deterministic automaton, right? So when I'm saying Büchi automaton, I will start with non-deterministic Büchi automaton, and I will define later deterministic Büchi automata also. Here it's a very similar, the definition is very similar to finite state automata. And now the delta, as usual here, it's q cross sigma to 2 raised to k. Okay, so just like NFA, you have this thing. So now, more specifically, I will use, instead of f, I will use something called an alpha to define the acceptance condition. Clear? To define the acceptance condition, I'm going to use alpha. Now, alpha will sort of, it will specify, it will capture how a word is going to be accepted by this Büchi automaton, okay, an infinite word. Now, when you talk about a finite word, then what is the acceptance condition? Like there is a finite word, it will end in an accepting state. There is a run of the finite word of this automaton, it will end in an accepting state. But now when we are talking about an infinite word, then in the case of Büchi automaton, what we are going to say is that a run is good or a run is accepting if it visits some set of good states infinitely often. Okay? If it visits some state from a set of good states infinitely many times. Okay? That's what the condition is. So just before I get into the acceptance condition, I'll also say what is a DBW. It's very standard. So if Q0, it's a singleton set, and for all Q belonging to Q, for all A belonging to sigma, we have that delta of QA equal to 1. Clear? So you have a deterministic transition. Okay? And every transition is defined. So the delta function in the case of deterministic Büchi automaton, it's a total function, whereas in the case of non-deterministic Büchi automaton, it can be a partial function in the sense that I'm saying that, well, I mean, yeah, I have defined it in this way, but I mean, sometimes like, yeah, right? I mean, in the sense that this could also be an empty set. So I'm not really defining, for example, on this part from this particular state, when it reads an A, where all it's going. Right. Yeah, it can. It's yeah, you are right. Technically, it's a total function, but it can also go to a set of empty sets. Okay, so a run of an automaton, as usual, the run of the Büchi automaton it's a set of sequence of states, right? Q0, Q1, blah blah blah. It's like an infinite run here, and Q0 should belong to capital Q0, right? And we define so run. So I will call this run as, let's say, run R is like this, and I'll say inf of R. What is inf of R? Inf of R is a set of states Q, right? It's a set of states Q such that Qi equal to Q for infinitely many i's. Okay, and here I should also say that alpha here is also a subset of Q, just like as you have in DFA. Alpha is a subset of Q. And is the definition of inf of R clear? Yeah. It's a set of states which are visited infinitely often, right? And now I say that the run R, So here alpha is a set of, like it's a set of, you can say it's a set of good states. Okay, sometimes people will also call them accepting states. So we'll call them good states. Now a run R is accepting, as I said. When will it be accepting? If that run visits some state in alpha infinitely many times, right? So then what is the condition? Like, can you state it formally? So I have defined alpha, I have defined inf of R.
If one intersection alpha is one.
Sorry, tell me again.
If
So a run is good or accepting. Run is good or accepting if
our intersection alpha is non-active.
inf R intersection alpha is not empty. Clear? So this is the notion of a good run or an accepting run. Okay? And I say that a word is accepting if there is an accepting run corresponding to that. Okay? Clear? So now I can say when a word is accepting. Okay. So now I can define a word, omega word W, right? When I'm saying word in this context, it's an omega word. Omega word W is accepting if it has an accepting run, just like a finite state automaton over the finite words. And then I can also say a language L accepted by this automaton is the set of such omega words which have some accepting run. Okay, clear? And if you consider a DBW, it will have a single accepting run. A deterministic automaton, it will have a single accepting run. Okay, so any questions so far? Any questions so far in the definitions, like even from the online participants? Okay, somebody is waiting. Okay, so, and we are going to talk about, we are going to define something called a omega regular. Just something like, there's a notion of regular language. What is a regular language?
Language which has an automaton which corresponds.
Yeah, so a language called a regular language over finite words is one which can be accepted by a DFA or an MFA, right? An omega regular language is one can be accepted by a non-deterministic Büchi automata. Okay, why I write W? Because one can also consider automata over trees and other kind of things. Okay. Okay. So here we are going to restrict ourselves to automaton over words, right? So non-deterministic Büchi word automaton. So we'll call them NBW, right? So sometimes if we are going to talk about non-deterministic Büchi automaton over trees, I might say NBT for trees. Okay, here these are words. Okay, clear? So this is the notion of omega regular language. So again, what is an omega regular language? So corresponding to that, there should exist a non-deterministic Büchi word automaton which can accept this language. Okay, so this is just a definition. So now let's look at some examples of non-deterministic Büchi word automaton. So when I'm defining this omega regular language as the class of languages which can be recognized by NBW, so do you have any question? Like, does any question come to your mind? Anybody? Huh? So that we will talk about, of course. But just from the definition, like for example, when you talk about regular languages over finite words, so what is the definition again? Accepted by a DFA or an NFA.
Cannot be accepted. May not be all that is accepted by the TBM.
Exactly. So we will see that there can be languages which can be accepted by an NBW, but they may not be accepted by a DBW. So which means that DBW form a strict subclass of NBW. Okay, so we will see that. Okay, good. So now can you try to have, so my sigma is, let's say, A comma B. So all of you, even those who are online, can you try to construct an NBW which will accept infinitely many A's, right? Can you try that just for a minute?
I think that if we have an NBW and a word,
Hmm.
is it decidable that if it is accepted by the NBW? Because there are like infinitely many paths.
There can be infinitely many paths.
And we just need one accepting path. So is there a way to decide if the word is accepted or not?
Yeah. So essentially, like if you consider, let's say that, so let's look at, there is this inf of R, right? So since we are talking about, this is like a regular language, right? So there will be some kind of a regularity behavior which we'll find.
Like some cycle or
Yeah, there will be some kind of a cycle which you will see that when the word is being read, there will be some kind of a cycle. I mean, in general, like you can have some word, arbitrary word also. I mean, the thing is that as long as, like, okay, so when you were say that if I'm able to figure out, the thing is, I mean, I have to, yeah, one thing is that I can construct just like, for example, like if I give you the same problem, right? In the case of a DFA, let's say, uh, there will be one way of doing it is that you just run it, okay? Or if I give you an NFA, you can kind of consider all the possible runs and see that whether it is seen infinitely often, right? Now, in this case, sorry, I mean, in the case of over finite words, it will end after some time, and you see that whether it ends in an accepting state. But now, here it's an infinite word, right? You cannot run it forever. If it's a decision procedure, you cannot run it forever, right? So one way to do this is like can you construct corresponding to this word? Let's say if it has some regular pattern, consider an automaton, and then check whether this automaton which will be accepting the single word, their intersection with the original automaton, is it empty or non-empty? That is one possibility. Okay, right. So yeah, so can you try to so this is this language I'm talking about, infinitely meaning is, can you try to draw the automaton corresponding to this?
State for A and the state for B,
Okay,
and both are starting states.
okay,
And like if from the A state, if you hit A, you put a loop.
okay,
And from A state, you can go to the B state when you see a B and vice versa. And the final state will be your A state.
okay. So here you have like, and then you were saying if I need A, I go there. If I need B,
And both are starting states.
both are starting states. Okay, why do you need both are starting states?
So the word can start with your.
But here also I'm starting with both A and B, right? So if this is my initial state,
Okay,
Doesn't matter.
right?
Okay.
Then I can start with both A and B. Clear? And then what is the set alpha here?
A state.
This one,
Yeah.
right? Clear? Now, if I say, for example, finitely many A's instead of infinitely many A's, how can you do that? Finitely many A's. So after some point of time, you are not going to see any more A's. How can you do that? After some point of time, you are not going to see any more A's.
We will add a third state.
And at some point it should come and stay in the past.
And then it should stay in that state again. That will be the acceptance.
So you are saying at some point,
So from both the states,
yeah,
we will add a transition to this third state.
okay, you
No,
need
we
a,
just have two states,
okay,
and the first state will have up to some point,
okay,
A comma B,
okay,
and then at some point it goes to the second state and stays on B.
reading a B,
B.
right?
Yeah, yes.
Good.
You
So
can
you,
even read a name, but yeah, reading a B can go there.
yeah,
That-
sure. You can also, you are saying that I could have also done a A here.
Yeah,
I mean,
but then
sure.
after that,
Right.
it will be a B.
Okay. Okay, fine. So, yeah, right. So now you see that this is, whereas this is a DBW, this is a deterministic Büchi automaton, this is an NBW, correct? The one that you suggested, it's an NBW. Now, can you try to think of, can you try for a minute and see, okay, that is wrong. What is,
So you said something else before that.
Hmm.
Like,
sorry, let me, okay, so what is said, okay. So is it correct now? So up A and B on transitions. Okay. Yeah, I mean, you have to tell me exactly what, I mean, now it's correct, right? Okay, good. Okay, fine. Right. So now can you try to find DBW which will have finitely many A's? Can you try to construct a DBW which will have finitely many A's?
But how, in that case, we need like
Yeah.
some number of states where the thing goes to, because finite, like how will you know where it ends?
How will you know where it ends, right? And so this is like a non-deterministic transition. So we are kind of non-deterministically guessing that this is the position after which no more A is going to happen, right? It's like a non-deterministic guess that we need to do. Now, what we will see that in fact, there doesn't exist any DBW for this language, okay? We'll see later that no DBW for this language. Clear? Okay. So this gives us the idea that DBW are strictly less expressive than the NBW. Okay. Good. So so then I'll just take it here. Not all omega regular languages are DBW recognizable. Okay. Fine. Okay. Now, just a small comment here, which is like for every run R, the set inf of R. You recall what was inf of R? This is a set of states which are visited infinitely often in the run R. So this is an SCC. It's a strongly connected component. Right? The set inf of R is a strongly connected component. What is a strongly connected component? It's like a set of vertices in a graph. A strongly connected component is a set of vertices with some edges and all, such that you can go from each vertex to the other vertex. Right? So inf R is a strongly connected component. Clear? So this is very easy to observe. Right. So now we'll look at the closure properties. So union of NBW. What do you think? How do you do the union of two non-deterministic Büchi word automata? What if it is two NFA? How do you do the union?
The two automata.
Just have the two automata in parallel. Will that work for NBW?
Yeah, because
It will work, right? So you just have two things in parallel. You have the union of the states, the union of the transitions. And if there is one run which is accepting, then it will also be accepted in the union over, right? So I just wrote it down. Nothing sort of. One second. Yeah. So it's just that simple. So you just take the union of everything. Okay. So that is that. Okay. And how many states does A have? It's the summation of the number of states, Q1 plus the size of Q1 plus size of Q2. Good. Now, what about intersection of NBW. So how do you do intersection of DFA again, let's say, or NFA?
We just take the cross product.
You take the cross product and
And the final states are the final states of both, like F1 cross.
F1 cross F2, right? So F1 cross F2. So let me take. So what is the guess now? Will it work? So anybody from among the online participants, will it work? So if you take the intersection, the cross product of two NBW.
No, that means that both the final states occur at the same time.
Both the final states occur at the same time.
That's not necessary. So it's like final state of one into all states of other. Union, final states of other, and all states of other.
That is what, like, so final state, that will not give you, that will give you the intersection, like.
That will accept if it's one final and other non-final.
Right? It may be the case that there is one accepting run here, which is not accepted in there is a word which is accepted in one, which is not accepted in the other one, or vice versa. Right? I mean, we are talking about intersection. Right? So indeed, what you were saying, it's correct. Like if you just take blindly and your intuition is correct. If you just take blindly this cross product, it's not going to work, right? So look at this. So both these two Büchi automata, right? Here A1 and A2, they accept the same language, which is just A omega, right? But now you see that this is the accepting state, the alpha 1 for this A1 and alpha 2 for A2 is like this one. So if you take the cross product, so the F1 cross F2, it's the empty set, right? It's not exactly accepting the intersection length. The intersection should also be A omega, the same as the language of A1 and A2, right? It doesn't work that way. So what can we do? What can we do? So I'll give you a hint. We can make two copies of the automata. We can make two copies of the cross product. Two copies of the cross product.
Okay. So one copy should ensure that A1 accepts it, and the other copy should ensure A2 accepts it. So in the first one, the final states will be the final states of A1 and any other state of A2.
Okay.
Oh, but we want both of them should have.
We want both of them to be accepted. Right? So you are having the cross product. You are having the cross product. So if there is a run in the cross product, that means that it is running on actually simulating the run on both the automata together. Right?
Yeah.
Correct? And I just want to ensure that both alpha 1 as well as alpha 2 are visited. Both of them are visited infinitely often. How can I do that? I can do something like this. That you start the run on the cross product, right? It's simulating the run on both the automata together. And then you see that you visit alpha 1 once, maybe, and then you wait to visit alpha 2. Okay, you switch kind of like from one copy to another. Okay, I go and I wait for alpha 2. And then again, once I visit alpha 2, I come back to the first copy. I wait to visit alpha 1.
Okay.
Okay, so that way I will ensure that both alpha 1 and alpha 2 are visited infinitely often. Once I visit alpha 1, I'm waiting for alpha 1. I visit alpha 1, I switch to the other copy where I visit alpha 2. Once I visit alpha 2, I come back to the first copy and I wait for visiting alpha 1. Clear?
Yeah.
Good. So can we do the formally can we try to write this? So how do we do that? How can we write this? So as I say, now my Q, I have two copies. Q1 cross Q2 cross 0, 1. Okay, I have two copies, and my Q0 will be Q1 0 cross Q2 0 cross 0. In the first copy, I have the initial state. I start from the first copy. Doesn't really matter. I would have started from the second copy also. It's just alternating, right? The run moves from the first copy to the second copy, and from the second copy to the first copy, and it just goes up forever, right? So now, what will be my, let's say, Q1, Q2, 0, comma A, right? So how will it be like? So suppose I have, so I'll say this is of the form Q1 prime, Q2 prime, 0, where Q1 prime belongs to delta of Q1A, Q2 prime, sorry, Q2 prime belongs to delta of Q2A, and Q1, since I'm not changing the copy, Q1 does not belong to alpha 1. Okay, Q1 does not belong to alpha 1. And if Q1 belongs to alpha 1, then what I will have? Q1 prime, Q2 prime 1. Okay? And similarly, you can also have delta of Q1, Q2, 1, comma A, right? So it's actually the set of like these states, the set of such states, right? Like this. Okay. And similarly, you can also define the other. Clear? So I'm not writing. Okay. Okay.
So Q1 or Q1 prime, which one belongs to alpha?
Sorry.
Q1, is it Q1 belongs to alpha 1 or Q1 prime machine?
Q1. And here, right?
Okay.
Okay. Yeah. So if I have already seen this alpha 1, if I have already come to alpha 1, from there I will go out to the second copy. Right? So if Q1 is in alpha 1, I'm going out to the second copy. Clear? Okay. Okay. So, and I can also define my alpha to be, let's say, alpha 1 cross, so I can just say that only in the first copy, when I come back, that will be my accepting, because anyway I'm alternating, I'm just forcing that. So if I visit the alpha 1 of the first copy, that itself should be fine. Is it okay? So I can say this is my alpha.
Okay, it is the current simulation.
Right? Because I'm alternating from that. I'm going from the first copy to the second copy, I'm coming back from the second copy to the first copy. So if my alpha is defined in this way, alpha 1 times Q2 plus 0, then I'm fine. Clear?
Well, are there allowed epsilon transitions in variable?
So here we are not talking about epsilon transitions. Okay. Yeah. So we are just, in this model, we are not talking about epsilon transitions. Okay, good. Now, one of the things is that what if I have dBW, if you see that if my A1 and A2 here, if they were deterministic Büchi word automata, the product construction, it sort of retains the determinism. The product construction does not introduce any non-determinism, right? So dBW are also closed under intersection. Clear? So DBW are also closed under intersection. Closed under intersection. What about union? Are DBW closed under union?
Yeah.
How?
Okay.
Right? The previous construction which we saw for union, putting them together,
No.
it introduces non-determinism because you have different initial states and things like that, right? Which can have different rounds. So are they closed under union?
You can just take the cross product
Yes.
and then the final states will be like the final state of one and end state of union.
Right. Right. So does it work, or do you still need 2 copies or things like that?
No, it can go.
It will work, right? You don't need 2 copies
Yeah.
because it's just the union. So as long as like you are either visiting one, either the alpha 1 or the alpha 2, you are fine. Clear? In the case of intersection, you have to ensure that you visit both of them. Here, as long as you are visiting one of them, right? Clear? The alpha is like alpha 1 cross Q union alpha 2, just like DFA union, which we do with product construction. Okay, good. So DBW are closed under unions. Yes. Right. So now let's talk about complementation. The complementation of DBW. So we saw an example which is like L has infinitely many A's, right? L has infinitely many A's. Language of infinitely many A's. So how will it look like? Right, so I have already drawn it. Let me see. Right. In the case of DFA, what do you do for complementation?
Just swap the final states and non.
Swap the final and the non-final states.
Yeah.
Right. Now this was the automaton we saw for infinitely many A's. Now if we swap the final and the non-final states, what language do we get?
The language is infinite.
Infinitely many B's. No longer we are getting finitely many A's. We are not getting that, right? We are getting infinitely many B's. So the thing is that that swapping the final and the non-final states, that does not work for DBW. Okay, but we can do something. Okay, we can do something. We can try to do a complementation of DBW. So we also noted these, right? Like that the complement language that W has finitely many A's. We just made a remark that there doesn't exist any DBW corresponding to that, right? Finitely many A's cannot be accepted by any DBW. So hence, DBW are not closed under complementation, right? So not closed under complementation. So this is something we saw, which means that given a DBW, let's say A, there doesn't exist another DBW necessarily, which will accept the complement language, complement of the language LA, correct? Now, I am claiming that you can do, sorry?
Is it omega regular?
Yeah, exactly. So that's what I was going to say. That now if you take the complement, can you construct an NBW? So you have the DBW, you are given a DBW, and I want to get an automaton. It can be an NBW, but it should recognize the complement language.
So that means after a finite run, it won't visit any of the
Yeah,
alphas in the
right. So what can you do?
So we can make another copy of the.
Very good. You can make another copy. Huh.
And in that, there will be transitions. Okay, in that we'll basically delete the alpha state.
Very good. Right.
And the same copy will move it.
Very
and
good.
there will be transitions from the first and second.
There will be transitions from the
From the first automator to the second and
first copy to the second copy.
Yeah.
But no, not back.
Backwards.
Right?
Yeah.
Nice. Okay, good. So this is what we can. Is it clear? Like what was said? So you have two copies. In the first copy, you have all the states. Then sometime non-deterministically, I will jump to the second copy. In the second copy, there are no alpha states. Right? I'm not going to visit that anymore. Right? And I'm jumping non-deterministically. Right? So I'm introducing some non-determinism. Right? And what is the set of accepting states? What is the set of accepting states in the construction that you mentioned?
Any state in the second.
Any state in the second copy.
Yeah.
Right? Any state in the second copy. So I'll just try to write this formally, maybe. Right? So let's see. So if you are given the automaton A, so I'm constructing the A prime, which is the complement BW. So you have, let's say, Q prime, sigma, Q0 prime, delta prime, alpha prime, where the original automaton A is like sigma Q0 alpha, right? So now, can you define what will be my Q prime? Q cross 0 union Q minus alpha cross 1. Clear? This is what exactly it said. And my Q0 prime equal to Q0 cross 0. Okay. Now suppose my delta QA, that is in the original automaton, if this is Q prime, right? So now how do I define delta prime of Q0 comma A? How do I define this?
Q is in alpha, then it goes to Q prime comma 0 or Q prime comma 1.
In either case. Okay. Yeah.
Okay, if
Yeah.
okay, so if Q prime is not in alpha, then I can either stay in this copy or I can also jump to the other copy. Okay, and if Q prime is in alpha, then I have Q prime 0, if Q prime belongs to this. And similarly, I will also have, let's say, delta prime of Q1A equal to Q prime comma 1 if Q prime does not belong to alpha, right? And this is the empty set if Q prime belongs to alpha, right? So such foundations defined. Clear? Good. So now the question is that,
sir, I have a question.
Construction for NBW.
Sir, I have a
For doing the
question.
complementation. So what are we doing? What did we do? We were given a DBW. We said that DBW are not closed under complementation because there are languages which, if you take for which there exist DBWs, and then if you take the complement, if you consider the complement language, there doesn't exist any DBW for that, right? And but you can always construct an NBW which will accept the complement language. And now the question is that this particular construction, which gave us that NBW, can you also apply that on an NBW? Anybody among the online participants? So was the question clear? It would work. So let's consider the cases. Suppose there is a word which is accepted. Let's say there is a word which is not accepted by the given NBW. We are trying to do a complementation. You take the complement automaton. If it is okay, so you can yeah. So I'm just repeating the question. So I'll just so the question is that right now we did a construction, right? We did a construction about complementing a DBW. We did a construction for complementing a DBW, and as a result, we obtained an NBW. What we did was like we made 2 copies of the DBW, and then we said that there is a non-deterministic transition from the first copy to the second copy. The second copy doesn't have any alpha states, right?
Yeah.
Okay, so this gives us a complement automaton of the DBW, and the resultant automaton is an NBW. Now I am saying that instead of a DBW, start with an NBW and do the same construction. Are you going to get a complement automaton? Are you going to get an automaton which accepts the complement language? Is that clear, the question? Saina? Yes? Okay, good. So now what is the answer? So the question is clear. Now what is the answer? So anybody wants to guess? Like what is the answer among the online participants also? Anybody wants to guess?
Actually avoid alpha. But in our condition, we can just ensure some path eventually. Like what we did,
Mhm.
ensures that some path eventually avoids alpha.
Avoids alpha, right?
But we want all paths should avoid alpha.
Very good. All paths should avoid alpha, right? So suppose if the word is not accepted by the original automaton, right? Which means that all paths are avoiding alpha, in which case the complement automaton will accept, because all paths will avoid alpha, they will go to the second copy and you will accept, right? So this is fine. If the original automaton doesn't accept a given word, in the complement automaton that we are constructing, it will accept, which is fine.
Yeah.
And
If a word accept,
if a word is accepted by the original automaton,
then it would still have a non-accepting language.
it can have an accepting run, it can also have a non-accepting run. But that non-accepting run will not visit the alpha. So now in this construction, what will happen? This non-accepting run will go to the second copy in this complement automaton and it will get accepted, right? So there is a one-sided error, correct? There's a one-sided error. If the word is accepted in the original automaton, it may still get accepted in the complement automaton that we are constructing, right? So this construction does not work for NBW. Clear? Okay. So is it clear to everybody in the online participants? Is it clear? I'm not getting any reaction, but okay. Yeah, if it's not clear, so the other thing is that I have also, so could you join the class Google Classroom? Okay, so I have created a Google Classroom, and so yeah, I mean, I was supposed to kind of talk about it today, but she sent already an email. So yeah, if you want to kind of get updates about the course, or if you want to join the course, then do send me, I mean, for all the online participants also, do send me an email, then I'll just add you, or I'll send you the invite link with which you can join the Google Classroom, right? So I'll post notes there, and there can be some discussions and things like that, right? So and also I will kind of add the lecture notes which I'm following for these lectures and things like that, which you can. So it's best to, I mean, it's not too big. It's best to just go through the notes after the lecture, right? right? Good. So, oh, the speaker is not working. So, Shantan, are you able to? Okay.
No, it's
Oh, I see. The speaker is not working.
Maybe
Okay.
volume is too.
I see. Okay. Yeah, maybe.
So maybe you could increase the volume on it.
No, I am actually using.
Or I think you can test if your speaker. Test speaker. We can't hear it. Maybe try changing system. There are
Our,
some other might work.
maybe it's blue.
Uh,
Now test speaker.
can somebody say something along the
You
audio?
can just give that.
You can just
Oh,
click
okay.
on this.
No.
No.
Like,
No, that is
center, that volume on between.
Okay.
Built in oil.
Hello.
It's the same. There may be.
Like one of us will probably join our phone and thing. But then they go
Yeah, what I can do is,
disconnect from here.
yeah, what I can do is that I can join with my iPad audio and disconnect from here. But I don't know how the speaker here will be. So the speaker is not okay. The speaker is not working from here. How do I disconnect audio here? Please. I think it was muted. Okay, so now can you hear us? Can you hear us? Can you hear me now? Okay, great. Thanks. Can somebody say something? Can somebody? Shantan, can you say something?
Yes.
Good.
Hello. Can you hear
Hello.
me?
Yeah, now I can hear you. Good.
Yeah.
Okay. Thanks. Okay. So good. Okay. Thanks. Okay. So yeah, if there are any questions, so you just you can interrupt and let me know. Good. So this complementation procedure, what we found is not doesn't work for NPW. It works for DBW, though not for NPW. There is a one-sided error. Now, what we will do? Oops. What is happening? I don't know. Okay, something works. Okay, so now, so far what we were doing, it was all warm up, right? Okay, I mean these were some easy constructions, like there was nothing very difficult. So one of the major things that kind of people have worked on in fair detail, and we'll look at some approaches, it's this complementation of NBW. Okay. So why was it useful? Like in the beginning, we saw that you were talking about like automaton subset checking, right? If the language of one automaton is included in the language of the other automaton, in which case you would take the intersection with the complement. So complementation is important, right? So complementation is important, and you cannot also, and complementation of NBW is important because NBW is more expressive than DBW and it captures all of omega regular languages, whereas DBW accepts only a subset of omega regular languages. So if you want to kind of specify a language which cannot be accepted by DBW, you have to take this, you have to represent this with an NBW, and we need to consider, we do the complementation of NBW, okay? Just to keep things, remember the things. So, so now Büchi himself, so he did a he suggested a complementation procedure, Büchi's complementation. So this is doubly exponential, okay? So doubly exponential in the size of the states. So it's like 2 raised to 2 raised to n, okay? So this is like 1962, correct? Okay? It does exist. So NBW are closed under complementation. That's what we are going to see. But we are going to see some, like there are several algorithms. We are going to see some of them. Okay, so then there was somebody called Prasad Sistla who suggested Sistla et al. I mean, there were 3 authors. So this was 1962. Then it took almost 25 years, and he suggested something which is order 2 raised to order n square. Okay, so this is 1987. By the way, if you consider, let's say, NFA, right, over finite words, then the complementation, like what is the complexity that we are usually aware of? Like, what do we do in order to complement an NFA? Make a DFA and complement, right? And when I say make a DFA, what is the, there's an exponential, right? It's 2 raised to n, not 2 raised to n square, 2 raised to n. And then you can just switch the accepting and the non-accepting states. Now, by the way, okay, there is another detour which you should, I guess you know, but if you don't know, you should look at before we meet during the next lecture for everyone. So suppose if I so okay, so how do you do translate an NFA to DFA? What is the procedure called? Subset construction, right? So it's called subset construction, and it gives you an exponential blow up, right? If there are n states, you get like around 2 raised to n states. Now, if I claim that, well, I mean, this is not a good algorithm. I'm smart, I have a great algorithm, it doesn't require an exponential blow up, right? Am I possibly saying the truth, or what do you think? Is the question clear to everybody? Right? So we are doing subset construction for translating an NFA into a DFA, and there is an exponential blow up. Now I say I'm a smart guy. I have a very smart algorithm which does not require an exponential blow up. I have some other algorithm.
That's not possible.
That's not possible. Why? What is the argument?
Similar words or something like that. like,
So what is the general idea? I mean, what is the general idea?
That
Yeah, somebody is saying here, yes.
yeah, the transition definition only we have exponential, right? So
No,
Q
that is
Q
no, that is the algorithm. The subset construction algorithm suggests that you have these things. Like this is how you are constructing your DFA from a given NFA. But
what I meant to say is in transition for NFA, we say that Q cross A goes to 2 to the power Q, right?
that's true.
So
That's true. I mean, you are doing a DFA that you are right. Like, I mean, we are doing the DFA construction, like there can be so many states, but that doesn't really somehow logically conclude that I cannot have an algorithm which will construct a DFA which is sub-exponential in size. Okay. So there should be a valid argument for this. Right?
Is it that the NFA can be in 2 raised to n different states?
Uh-huh.
So you anyway, when you convert it into DFA, you will need 2 raised to n states.
Well, this is all like this specific algorithm is what it does. It keeps the subsets and all. But if I say that I might have a smarter algorithm, I mean, so this is how it goes. I mean, you should all go and sort of revise the things that you learned in your finite automated course. Is that like there can be a family of languages? So this is like a lower bound we are asking for. It's like a lower bound thing. We need a lower bound proof that any algorithm which does this translation will produce a DFA for some family of languages which will have exponentially many states, right? So there exists a family of languages such that if the NFA accepting those languages have order and states, then any DFA will have 2 raised to n states. Yeah, if I can show this for a family of languages, then if I claim that I have an algorithm, that is certainly not true. And this is how the lower bound proof. So I'm not talking about an upper bound proof here that give me a nice algorithm. I'm saying that this is something which is not possible by any algorithm, right? It's like a lower bound that we need to prove, right? And there exists a family of languages. So what is that family of languages? So just try to figure it out, okay? And so I also have some notes on this course that I had for theory of computation, automata and computability. So you may also find those details there, but it's available across the internet, right? So you should get to understand those details of the lower bound, and I think because we are going to talk about that in the next this thing, and we are going to talk about Büchi complementation. So we are going to see the upper bound, and then we'll also see what are the possible lower bounds for Büchi complementation. Okay, so that's why it's sort of a detour, but it's important. Okay, so we have 15 more minutes, and so then this breakthrough came the year after. So somebody called Shmuel Safra. We will also get to, if you're studying complexity theory at some point of time, you'll also get to hear about other results by Safra. So it's called Safra's determinization. It's not exactly a complementation procedure, but it's a determinization procedure. It gave 2 raised to n log n for determinization. Okay, so now I'm saying that what does it even mean for determinization? Because I'm starting from NBW, and can you really determinize it? Because DBW are, cannot accept, like given any NBW, there may not even exist a DBW. So Safra's determinization into something called, instead of DBW, now you get something called DRW. It's a stronger acceptance condition. It's called the Rabin acceptance condition, which we'll see maybe a couple of lectures from now. It's a different acceptance condition. It's called the Rabin acceptance condition. So Safra takes an NBW and gives you a DRW, deterministic Rabin word automaton, right? And so I'm still not getting the complement automaton, but then there are again some other kind of acceptance. So you can just do some kind of like minor. When I say minor, it's like easy changes so that the DRW can be complemented and can be seen as something called a street acceptance condition, and then it's so this is what he suggested. It's still a deterministic automaton with a different acceptance condition. Now, then, like in 1991, so there is somebody called Clarland. He uses progress measure in 1991. This came. So the idea of the progress measure is like it's a generic concept. You will get to see the notion of progress measure across different things. So at each step, we are going kind of like there's a computation and we are kind of going closer to the goal. So that's the idea of a progress measure, right? And then there is some work by Kupferman and Verdi, and we are going to see today, starting from today and in the next lecture also, a modified version of this particular construction they have. They use something called ranks, and this work came in 2001. Okay, it uses this work, the original work, it uses alternating. So do you know what is an alternating automaton? Do you know what is an alternating automaton? And this is something, again, if you're studying finite automata in some detail, you will get to see them. So what is a non-deterministic automaton? A non-deterministic automaton is an automaton such that from every state, there exists some run which needs to be accepted in order to have a word being accepted. You always talk about there exists a run from that state. I can also think about some automaton where I say all the runs from a state have to be accepted. It's not just one run. I can define my automaton. I can define my automaton in a way such that there are multiple possible runs, but all of them have to be accepted. Only then I will accept the word. Right? So this is called an universal acceptance condition because it's like for all. Whereas non-determinism is like there exists an accepting run. It's an existential condition, and here I'm talking about for all, universal. So are you able to hear me, all who are online? I mean, I just want to, because we changed the speaker and the microphone. Are you able to hear me now? Yes, okay, good, thanks. So, okay, thank you. Right. Yeah, it's a big yes, so that's good. Okay, so now the alternating automaton is one where you have states which are of both the forms. So you have existential states, which means that from this state, if I have multiple successors, right? So let's say I have successors, right? And I'm reading, suppose, an A here. So I have A successors. Then if this is an existential state, then along some successor, I should be able to accept. And here, if this is an universal state, so an alternating automaton is one where you have a mix of existential and universal states. And here, if I'm reading a B, so these are my B successors, then I have to accept along all the successors. It's a mix of the non-deterministic existential and universal.
Should the path be like existential or like should it alternate with the existential and all the paths?
Not necessarily. The states can be in any form. Like you can have, this can be again, let's say, existential. It's not necessarily that you have to alternate, but it's a mix of different kinds. So non-deterministic automata is a special case of alternating automaton where the set of universal states is empty. Okay? And universal automata, if you want to call it, like which has only universal states, that's also a special case of alternating, right? And a deterministic automaton is both non-deterministic as well as, I mean, it's an alternating automaton also because we just have a single run, right? Good. So yeah, that's slide D2, and I did not yet talk about what is a Büchi automaton. It's again another acceptance condition, right? Which we'll also learn. And what we will do is that we are going to skip this thing like this alternating Ko-Büchi automaton, but we'll use all these ranking functions and all. We'll have a direct construction and we'll see how to get a complement automaton for the non-deterministic Büchi automaton to another non-deterministic Büchi complement non-deterministic Büchi automaton, right? So that is this. Oops. I think. Okay, good. So now I will call it a modified. So we have roughly 10 minutes. Modified Fuhrman-Vardy construction. Okay, so what is this modified? So I'll say this is my NBW, Q sigma delta Q0 alpha, and I'll say, let's say Q equal to N. Okay, and I have a word W, I will have A1, A2. It belongs to sigma omega. This is an infinite word. And I consider an infinite. So these are a bunch of definitions. We'll just define and then we'll finish the lecture today, and then we'll continue with the actual construction and the proofs in the next lecture. So we have an infinite DAG consisting of all runs of A on W, right? There can be multiple runs. So I will consider a DAG, a directed acyclic graph, which will kind of capture all the runs. There can be, of course, infinitely many runs, right? There can be infinitely many runs. But the idea is that I'll start from the set of initial states at some at an initial like a level 0, let's say, and then it's a DAG. So at any level you won't have more than n such states, right? So you will have at most n states. Clear? And the run, essentially, it's like, what is my V? So in this DAG, it's the Q cross N, okay? Where Q is the state and N, this is like the label, the level number, right? So it's the union of QL. I mean, yeah, like QL is the set of states at level L, and where L is the level number, right? So this is this thing. And what is my QL plus 1? QL plus 1 is Q belonging to QL and delta Q comma AL plus 1. Okay, so this is my QL plus 1. And what is my E? E is a subset of 0 QL cross L, right? Cross QL plus 1 cross L plus 1, right? So it's like this, such that I have E Q L. So there is an edge from QL to Q prime L plus 1 if and only if Q prime belongs to delta of Q comma AL plus 1. Clear? So this is, I'm just constructing the whole DAG, which sort of shows the entire set of like all the sets of all the runs. And so as I said, that there are few things here to note. At any level, there are at most n vertices in the DAG. At any level, there are at most n vertices. And we call an alpha vertex. So it's a definition. So QL is an alpha vertex. Is an alpha vertex if Q belongs to alpha and right, and so we say G is an accepting run DAG, right? So G is the DAG, it's an accepting run DAG if there exists an infinite path that visits infinitely many alpha vertices, right? Infinite path, I mean, there exists a path which is an infinite path with infinitely many alpha vertices. Many alpha vertices. Okay, otherwise G is rejecting. Right? And A accepts W. I mean, this is easy to see if G is accepting. Okay, so this is just, and so now there is one question I can ask. So suppose you consider the run DAG and there are infinitely many alpha vertices. Clear? So there is a run DAG. There are infinitely many alpha vertices. So you have this DAG corresponding to a word W. So when we are considering the DAG, it corresponds to some input word W, and we are considering all the runs, right? Now, suppose in the DAG there are infinitely many alpha vertices which are appearing. Okay, so is it clear? Like what I'm saying? In the DAG there are infinitely many alpha vertices which are appearing. The question is that, is it true that the DAG is accepting? Is it clear? The question is clear. So in the DAG, there are infinitely many alpha vertices which are appearing, correct, corresponding to like an input word W. Is it true that this run DAG G, it's an accepting DAG?
There could be a cycle that doesn't involve any of the acceptance states. No, it can't have a cycle.
So it's clear, like what I'm saying, that the DAG, it's an infinite, like you have infinitely many levels, right? You have level 0, level 1, level 2, like this. There are infinitely many levels, right? Like the way we define, like the set of states is in fact Q cross N, right? So it's actually like well, it's like this, right? And you have the edges here. Like I also defined how the edges are, how the edges are. The edges are defined like this from one level to another, right? Now my question is that I also defined what is an alpha vertex somewhere, right? Yeah, alpha vertex is something if Q belongs to alpha, right? So you have it's a tuple of the state and the level number. If Q belongs to alpha, the state belongs to alpha, then the vertex QL, I'll call it an alpha vertex. Now I'm saying, suppose there is a DAG which there are infinitely many levels, right? And suppose there's a DAG which has infinitely many alpha vertices, correct? Infinitely many alpha vertices. The question is that, is it true that the DAG is accepting? When do I say that the DAG is accepting? Like if it has an accepting run, right? There is an accepting run, that means there is an infinite path. An infinite path has to exist, which will, in that infinite path, there will be infinitely many alpha vertices, correct? Okay, so that is when I will say that the DAG is accepting. Now I am saying that given any DAG, there are infinitely many alpha vertices are there. Is the DAG accepting?
So there is some path with infinitely many.
Yeah. Can you construct an infinite path which will have infinitely many alpha vertices? Anybody wants to among the online participants? Like, any guess? So this is the last thing, and then we'll stop.
Let's say there are infinitely many paths in it, and each one has only a finite number of acceptance.
Okay. Okay, good. Yeah, sure. So I think you are right. So given the fact that the DAG has infinitely many alpha vertices, it does not necessarily imply that you can find a path which will have infinitely many alpha vertices. So there are infinitely many paths, right? And each path can have only finitely many alpha vertices. So that does not imply that G has to be accepting. Clear? So we can just quickly see an example. So suppose I have an automaton here Q01A. I go to this. Here, this is the alpha. This is Q1 belongs to alpha. And now I have Q2, and this is the thing. So any run you consider, any single run you consider, any infinite run you consider, will not visit the alpha vertices infinitely often. It will visit an alpha vertex only once, right? So even if there are infinitely many runs, right? There are indeed infinitely many runs. You can take this loop before, so I mean arbitrarily many times before you take this edge, this transition, right? So there are infinitely many runs, but each run visits an alpha vertex only, I mean, visits this vertex Q1 only finitely many times, just once, right? So there doesn't exist any infinite run or any infinite path in that DHG which will have infinitely many alpha vertices on its path, right? So the DAG being infinite with infinitely many alpha vertices doesn't necessarily imply that it is an accepting, right? Good. So let's stop here. And so those who are interested to continue, so we are meeting on Monday at 11:30. So you can send me an email. You have already sent. So, and I will add you to the Google Classroom so that even if you want to get some updates, I mean, offline, so you can get them, things like that, right? So, yeah. So let me end. Are there any questions? Are there any questions from the online participants? Anybody? No? Okay, so then, okay, so I'll just maybe mention, which I'll also post on the Google Classroom, that there is this, so these things that I'm doing, so they're all from something called, so there is a book, it's called the Handbook of Model Checking. So it's a fairly recent book. I think it came out only around 2017 or 18, around that time. And there is a chapter by Orna Kuferman, right? I mean, the one who had suggested this construction that we are going to look at. So Orna Kuferman, and she has a chapter on automaton on infinite words. And if you go to her homepage, like you just search for Orna Kuferman, Kupferman, and if you go to her homepage, you will also look at her papers. I mean, there's a page which has all her papers, and there also you can find this chapter. I mean, from the right automata. If you have any difficulty, then let me know. I'll also try to post it on the Google Classroom, the link to that PDF. Okay, but I would strongly suggest and recommend that go through those notes. It's not very long. It's just like a few pages. So every lecture will possibly cover only, like, let's 3 pages of it, and for the first half of the course. 3-4 pages, and then just make sure that you are going through that and understanding things in detail, right? So, okay, so if there are no more questions, then let's stop the recording